Initially, I would like to thank to the organizers of this event. I think it has been going really well, and I'm kind of excited for tomorrow as well. I'm Zeki. I'm part of QWorld and one of the founding members of Q Turkey. Also, I'm from the Middle East Technical University Physics Department, and this work has been done in collaboration with METU Science and Technology Policy Studies Department. And it's titled The Landscape of Academic Literature in Quantum Technologies. So if you have any questions, you can ask at any moment. Also, I've shared the archive link to the paper in Discord. You can check it from there as well. The work is recently published. You can see the published version as well through archive. So the outline of the talk is I will give a very brief background. I will introduce our methodology and what are bibliometric tools, our dataset, keyword analysis, and burst detection, core corpus, and discussion. And the background is basically like this. So bibliometrics is a kind of an emerging field, or it has been emerging for quite some time. And I think most of the academics here know what it is about, but for those who are unfamiliar with the topic, bibliometrics is basically the study of the academic literature landscape, which means, journals, citations, authorships, and how they are networked together. The field actually goes back to around 60s to a man called Eugene Garfield, who is one of the founders of what you might call today Web of Science. And if you are an academic, you have to deal with things like H-index or impact factor. You have to either thank or curse him. The main idea behind bibliometrics, or the initial idea behind bibliometrics, was that basically, since the number of journals were increasing rapidly, libraries, especially university libraries, had to decide which journals to subscribe and which journals to not buy for them. And Eugene Garfield basically provided this service, and it has evolved. And then especially in the last 2 decades, since let's say computational analysis became more easily available, everything became online and the field emerged. So we can actually study how scientific fields emerge, how they change, how they are interconnecting, what are the emerging topics and that. And the background of our study comes from Arsev Aydinoğlu. He was my instructor for the bibliometrics course. He had done a similar work on astrobiology, and we decided to do something like that for quantum information technologies, and later we changed the name to quantum technologies. So the methodology and bibliometric tools used in this work are like that. We determined the sample size and formulated a search query on Web of Science. We used Web of Science because it is a very neat data set. If you use something like Google Scholar for a work like this, there would be a lot of, let's say, junk papers or presentations or some things that you don't want in your data set. But Web of Science is very neat. We initially prepared a query by ourselves. We analyzed it, we sent it to certain experts, got some feedback, and by using the new query, we analyzed it, again asked the experts whether the results are, do they seem reasonable or not, and then we finalized the study. We also used something called highly cited articles that is provided by the Web of Science, which means it's not just the most highly cited articles, but it is highly cited articles that are kind of new. Let's say an article 3 years old is cited hundreds of times. It is accepted in the highly cited articles. And for tools, we used WOSWeaver and SciSquare tools. Both of them are free software tools that you can just download and use. They have good manuals. SciSquare tools is a little bit more harder to use, but it has more functionality. WOSWeaver is really easy to use, and I I actually recommend everyone, especially if they are doing as a PhD, they should check PostWeaver because it's a very fun tool. So our initial search query was this. This was our final search query. You can reach these queries through our archive paper. And initially we ran the analysis in 13th of March 2019. We found 41,000 articles and proceedings. Later, after modifications, we ran at 6th of June. I'm giving you these dates because if you run the same analysis today, you will reach a different number of papers. But if you run the same analysis with the same queries for that date, you will reach exactly the same number of articles if there are no retroactive papers. So this is you can replicate this study by yourself as well. And after getting the initial records, we curated the set, meaning that we got rid of certain papers that have 0 citations or 0 references. We can discuss on this point as well, but this is a choice. You may choose not to do it as well. And there were there were 495 journals with 5 or more articles from the dataset. So the number of articles in the field is rapidly increasing. You can see this is the total number of articles, and it is kind of not exactly exponential, but it is increasing really rapidly. And also, one of the other findings that we had is the co-authorship numbers are increasing as well. So per paper, the number of average authors has been increasing, and since 2013, it has been the mode of the number of authors is 3, meaning that the huge chunk of papers produced here have 3 or more authors. And this is our initial keyword clustering. We created this through our first search query and then send it to experts for feedback. And then by their feedback, we constructed second query, and the new clustering, since we used only the 60% version, it was like this. So here you can see, so this is a keyword clustering. You can actually, yeah, of course I can provide the slides. Actually, you can see that there are 3 clusters in the literature, which we interpreted as the red cluster is more related to physical hardware. So regardless of the topic that you are dealing with, if you are doing mostly experimental science, probably you will be in this cluster, or you will be interested in this cluster. This blue cluster is more on quantum communication, quantum key distribution, and single photon sources and quantum repeaters. So it is quantum communication and cryptography, and the green set or the green cluster is more towards quantum computation and quantum information science. And how can we say this? If we increase the number of keywords that are used, a fourth cluster appears, and actually you can see the fourth cluster is more on quantum information science and quantum thermodynamics, meaning that it is an if you look more precisely, you can find other clusters maybe, but these 4 are the main, and this yellow cluster, meaning quantum information science and quantum thermodynamics, is more closely related to quantum computing. So we used clustering for terms that are occurring more than 200 times in a set. So since we had 42,000 papers, so if the keyword occurred like, I don't know, 0.5%, then we included it in the cluster, but most of them were used much more. And you can actually see the figures for yourselves. The figures are also shared in the Figshare website. You can download the high resolution versions of them. And following this, we use something called a burst detection. Burst detection is an algorithm used by Kleinberg, or developed by Kleinberg, and it is not just a frequency analysis. It identifies sudden increases in the frequency of words. And Seskir also uses this open NLP framework, so it gets rid of the words like the, a, or common words. There is this parameter called density parameter. If you increase it, you get more keywords. If you decrease it, you only look for the huge bursts in the field. And for a low density parameter, you can find these. So as you can see, quantum computation is the first burst, and it has lasted quite some time, as quantum computing as well, teleportation, entanglement. But as time progresses, you can see that newer topics like quantum discord, quantum correlations, quantum optics is emerging. And this huge entanglement burst is a little bit weird as well. I will talk about that. And these are the bursts that were ongoing at the time that we collected the data set. And as you can see from here, like quantum coherence, simulation, networks, annealing, ADS-CFT, open quantum systems, all of these were, and some of them are still hot topics in the field. And probably if you run the same analysis today, we will see that maybe some of these have ended and newer topics emerged. And what we mean by ended, what does it mean that a burst ends? So to actually see that, I ran this frequency analysis by myself, not using the software. And here you can see, for example, quantum teleportation is not bursting here, right? But it has become mainstream. So it is steadily, like, it is around here. So if a burst ends, it doesn't mean that the topic is fading away. Maybe it has become mainstream and the frequency increase is not sudden anymore. It is just a linear increase, or it is increasing at the same rate, which means that you cannot just say by looking at the burst whether a topic has faded away or not. Also, you can see here that there is this huge quantum computing spike in 2009. We discussed, I think we discussed with Zoltan as well, regarding why this could be happening. There are many explanations, but I'm not sure whether any of them actually applies. And there is this highly cited articles section. Here, using our search query, we have found 808 published articles. And out of these, there were 34 which had over 30 citations in the set of highly cited articles. Meaning that out of these 800 papers, 34 of them were cited more than 30 times in the set. And we kind of presented these as a core corpus of the field. And by core corpus, I mean the academic works that are most used by others in the literature. For example, you can see that the Nielsen and Chang's book is cited 113 times in this set, and they are cited 6,900 times in our curated set. So the total citation number of this work is much higher, but in our literature, it has been cited these times. But also you can see that for top 5 core corpus in the curated set, they are the cornerstone papers or works like Nielsen and Chang, Bennett, Eckert, Gizin, and Einstein's EPR paper. But for the highly cited set, the most cited papers are more recent, like Kimball's quantum internet paper, Walraff's superconducting quantum qubit, Nayak's. I think this is about topological quantum computing, and the Horodeczky's paper. I think this is the review on quantum entanglement and quantum measures. And we ran a country level analysis as well. And here we have found that China, or the papers that are coming out of China with Chinese affiliations, are the number of them is the highest. But if you compare, China, US, and European Union, even if you exclude UK, the total number of papers are pretty much the same. At least at the moment we collected our data set. So we can say that they are on par. And here is a co-authorship analysis of countries with more than 10 published articles. You can actually see the clusters of collaboration here. You can look at this figure later. And on an institutional level analysis, we have again found that the Chinese institutions have the most amount of academic papers. And the Chinese Academy of Sciences is a special case here because some of the academics from China have multiple affiliations, and the software cannot distinguish between the differences of whether if you have two affiliations, the software thinks that there's a collaboration between these two institutions, and you can argue that there's a collaboration between these two institutions, but it kind of causes to overcount certain numbers. But if you just ignore Chinese Academy of Sciences here, you can see that the rest of the institutions are reasonable. And actually, we run an institutional collaboration analysis as well, co-authorship analysis of organizations with more than 150 published articles. And here you can see that most of the institutions from China are collaborating internally. Again, I think this is Taiwan, they are doing the same. Japan, they are doing the same as well. But other than that, there is this huge group, like this is Europe, this is Canada and Australia, this is US, and Russia and Singapore are have their own clusters, even though they are smaller clusters. So the discussion using bibliometric tools to examine the field of quantum technologies yields some valuable insights. The bursting topics evolve away from straightforward quantum computation into more diverse areas like quantum networks, quantum steering, quantum coherence, quantum correlations. Those are all emerging topics, or they were emerging topics. Maybe there are some newer emerging topics. And we can say that China, US, and EU have similar sizes of contribution to the academic literature in terms of number of papers. So this is not a qualitative contribution, but in terms of quantitative contribution, we can say that these regions are almost on par. And Chinese institutions tend to collaborate with each other more heavily than international. I've just shared these three references. You can check the papers from here as well. And I would like to thank you for your attention. Thank you, Ike. Okay. Should I read the questions?
Yeah, I can do that. Thank you, Zeki, for a very detailed analysis and comparisons and everything. It was a very detailed study. So you have some remarks for the excellent analysis. And there's one question from Andraj Palai. It says that, have you collaborated in the development of EU competence framework on quantum technologies?
I haven't collaborated, but we have been in contact with Rainer and Francisca for quite some time. I think I provided some feedback. They know of this paper. I've shared with Francisca, I don't know, maybe last year. So they're aware of the paper. I think we even cited them in this paper. I don't know. I'm not sure.
Okay. And then can we forecast something in quantum technology with the help of this matrix?
I mean, that was the idea, but one of the difficulties of this burst analysis is that, so first, for something to be published, I think you're already behind the wave. I mean, you are behind a couple of months, and you have to wait until the burst is apparent for the software to identify. So one of the ideas here is we can use like archive papers for this. So if you can run this analysis on archive papers, you can actually kind of forecast, or at least catch up to what is current. But to be able to run this same analysis with archive papers, I think we need a better data scientist than I am, because I'm not a very good data scientist. So if you, and archive papers are open, and by open I don't mean you can read these papers. Archive recently, or a couple of months ago, they opened their data set through Kaggle, if I'm not mistaken. So you can actually reach, you can choose by using categories and keywords, and you can run the same analysis on archive papers as well. So that will probably be more helpful in terms of forecasting what is going on.
Yes, thank you very much.